This is the section 4.5 extra examples on graphing rational functions. So we're going to start off with part C because I did not get to this in both sections. This is a pre-factored rational function, so everything's already been factored down. Notice that the x plus 1 on top and bottom is going to cancel out, which means that we are going to have, remember, a hole when something like that happens. Anything left in the bottom will be a vertical asymptote, and anything left on top with an x will be an x-intercept. So remember, when we graph these rational functions, there's some things that we want to know. We want to know the domain, whether or not there's a vertical asymptote. We want to know about x-intercepts, holes, the y-intercept, if it exists as well, and whether or not we have a horizontal asymptote or an oblique asymptote. Okay, so the vertical asymptote is found by setting whatever is still in the bottom that hasn't canceled equal to 0 and solving for x. So this is our reduced fraction here. So we would set 3x minus 7 equal to 0. That would be add 7 over and divide by 3. So that's going to be 7/3. That also is part of our domain restriction, as well as the -1. Remember, the domain is everything in the bottom that could have gone wrong and caused a 0. Whereas when we write them out later, we'll talk about how some things in the domain are vertical asymptotes and some things are holes. The x-intercept happens by setting the top part that still has an x equal to 0. So we'd subtract 3 and then divide by 5. And remember, that's an ordered pair, so -3/5 comma 0. The hole is found by setting the part that cancels equal to 0, which does give me a -1, but a hole is also a point. So we need to plug -1 into the remaining piece of the function to see what the y value is for that hole. So this is -5 plus 3 over -3 minus 7. That is -2 over -10, or 1/5. So that's where that hole is going to be. The y-intercept is found by plugging in 0 to the reduced function. So 5 times 0 plus 3 over 3 times 0 minus 7. That's just going to be a 3 over a -7. So that'd be -3/7 as a y-intercept. And then when we look at this reduced function, notice that the degree on the top is a 1 and the degree on the bottom is also a 1. So they have matching degrees. So that means it's a horizontal asymptote and you use the leading coefficients, so 5/3, which means we do not have an oblique. Okay, so we're going to take all the information that we have and we're going to try to plot this on our graph. So we know that we have an x-intercept of -3/5 comma 0, so that's a little bit over halfway between 0 and -1. Trying to make sure you can see the point. There we go. We have 0, -3/7 as a y-intercept. We have a hole at -1 1/5. Remember, that's where we put an open circle when we have a hole. So it's hard to see that, and I'll try to redraw it. So it's an open circle. And then we need, oh, it doesn't want to stay. Hang on. I'll have to overemphasize it. It's a little bit higher than it needs to be, but it's not wanting to stay when I draw it small. Our vertical asymptote is 7/3, so you'll probably want to divide that to get a rough estimate of where that is, which is about 2.3 repeating. So at 2.3 on the x-axis, we will draw a dashed vertical line. And our y, our horizontal asymptote is 5/3, which will be 1.6, I believe. Yeah, 1.67. So that is where my horizontal asymptote is. So this is y equals 5/3. This is x equals 7/3. Okay, so that's all of the information we have so far. So remember, when we set up our table, because we need more points than what we have here, we always look for x-intercepts and vertical asymptotes as markers for where we should be picking our x values to plug in. So the only x-intercept we had was -3/5, and that was the first thing we encounter along the x-axis. So -3/5 is an x-intercept. And then our next thing that's crossing the x-axis is this vertical asymptote of 7/3. So we need to pick values, probably around 1 or 2 in each region here. So something smaller than -3/5, well, we already have plugged in -1, so maybe we'll try -2. Something in between -3/5 and 7/3, we already have 0, so I'm going to try 1. And then something bigger than 7/3, so maybe 3 and 4, because I have a lot more points on this side already, so I'll try to get 2 over here. And then we just plug this in to what's left when we reduced. So 5 times -2 plus 3 over 3 times -2 minus 7. That's -10 plus 3, so that's -7 on top. That's -6 minus 7, so that's -13. This is +7/13. So that is still a little bit underneath 1. So that's going to be right about there. If we plug in 1, so 5 times 1 plus 3 over 3 times 1 minus 7. 5 plus 3 is 8. That's 3 minus 7, that's -4. So that's going to be -2. And then let's plug in 3. That is 15 plus 3, so that's 18. That's 9 minus 7, so that's 2, so that's +9. So 3, +9. And then 4 would be 23 over 5, which you'll probably want to get a decimal for that when you plot it. It's about 4.6. So 4.6. So notice what it looks like is that my graph is hovering in this corner in that region, and it looks like we're hovering down here with these boundaries. Now the only thing we want to double check is that there's no possible way that this line could cross that horizontal asymptote. And remember, the way to check that, and you can use your reduced function, is you set f of x equal to your asymptote for either, and it would be either your horizontal or your oblique, depending on which one you have. So this is to check and see if we cross our HA. So I say 5x plus 3 equals, over 3x minus 7 equals 5/3, which is my horizontal asymptote. We cross multiply. That would be 15x plus 9 equals 15x minus 35. Notice when you go to cancel out and move the x's over, they both cancel because they're both +15x, so we don't cross. So we know for sure that this is the correct graph without it crossing this horizontal boundary. All right, so let's look at another one. We're going to look at part D. This one we need to factor first before we can do anything else. So if I look at the bottom, I have x plus 1 on top. On the bottom, the factors of this would be x minus 3 and x plus 1. So we are going to get a cancellation here. This will be 1 over x minus 3. Okay, so when we look at this, we know we're going to have a hole, and I'll write that down in a minute. And we know we're also going to have a vertical asymptote because we have something left in the bottom and we had something that canceled out of the bottom. My two undefined values would be a -1 and a 3. The one that is the vertical asymptote is the one that's still there in the bottom. So x minus 3 equals 0 means x equals 3. I don't have any x-intercepts this time because no x's were left on top after we reduced. And then I do have a hole. My hole occurs at -1 because that's when x would equal 0 for the part that cancels out. And then we have to plug that back into the function to find the y value of that, which would be -1/4. Okay, and then we want to talk about y-intercepts. You can always use the reduced version, so if I plug in 0 for all the x's, that's just -1/3. And then we want to talk about either horizontal versus oblique asymptote. If you look at the original, because you can look here or you can look at the final version, the power on top is smaller than the power on the bottom. That means this does not divide in. The bottom cannot divide into the top. That's when we get 0 as our horizontal asymptote, or the x-axis if you want to think of it that way. So that makes sense why we don't have an x-intercept that works. So there's my y equals 0. X equals +3 is my vertical asymptote. I have a y-intercept of 0, -1/3, so that's down there. I have a hole of -1, -1/4, so there's a little open circle here. Kind of hard to draw. And then that's it for all that information. So now I need to look at the really only marker I have, since I don't have any x-intercepts, the only marker that I have that I need to use for separating my regions is this vertical asymptote. So I'm going to pick at least 2 points on each side just to make sure I'm checking everything. So let's pick something close to this, like a 2, and let's pick something a little bit farther away, maybe like -4. And then over here on this side, I need to pick something maybe 4 and 5. Okay, so we're going to plug those into our reduced function. That's -1/7. That would be -1. That's going to be +1. And plugging in 5, we get 1/2. So we're going to plot those points. -4 1/7 is pretty close to that asymptote. 2, -1 is right about here. Then we have 4, 1, and 5, 1/2. So it looks like we're staying in this region up here. And we're going to double check to make sure it doesn't cross the horizontal asymptote. And down here it looks like we're staying in this region. Now remember, not all of our rational functions have these two alternating pieces. We're going to, after this example, we're going to explore some that are a little bit different. But let's make sure we don't cross our horizontal asymptote. So we're going to set our function, the part that's left, equal to the horizontal asymptote, which is 0. And when we go to cross multiply, notice that we get 1 equals 0. So does not cross. So this would be the correct graph for that. All right, that leads us into another example, which is a little bit different. This will be the first time we get something where one of the sides is not going to be up and the other one's going to be down. All of our graphs so far on this video have had opposing shapes, essentially. But we want to look at one where maybe both parts are up or both parts are down, so that you see that you really do have to do test values and do the table of values. So this is already factored. If you want, you could write it as x plus 1 times x plus 1, but the x plus 1 squared takes care of that. This is just another way to write the same thing. So my domain, the only value in the denominator that's a problem is -1, because if that was a -1, this would be 0. It is definitely a vertical asymptote because it doesn't cancel out. We don't have any x-intercepts because there's no x's on top. We don't have a hole because nothing canceled out. Y-intercept, if we plug in 0 for the x's, that's 2 over 1 squared, which is 1, so that's just 2. Horizontal versus oblique. Oblique. Your degree of the top is nothing. There's no x's on top. If you FOILed this out, the degree of the bottom is going to be x squared. So anytime the bottom is bigger, that's when you get the x-axis as your horizontal asymptote. So no obliques here. So I'm going to go ahead and draw in what we know. So here's y equals 0. That's the x-axis. X equals -1 is the vertical asymptote. We have a y-intercept of 0, 2, so there's that point. And that's all that we know from this. So my only thing on the x-axis, even though this line is touching the x-axis, the only time we cross or have a point on the x-axis is at the -1. So that's going to be my separator on my table. So my vertical asymptote was -1. So I'm going to plug in maybe -2 and -3 and possibly +1 and +2, points that I don't already know. So then if I plug this in, 2 over -3 plus 1 squared is 2 over -2 squared, which that will turn into a positive on the bottom. So that's 2/4, which is a half. 2 over -2 plus 1 squared is 2 over -1 squared, which is 2 over 1, which is just going to be 2. 2 over 1 plus 1 squared is 2 over 2 squared, which is 2 over 4, so that's a half. And 2 over 2 plus 1 squared is 2 over 3 squared, which is 2/9. Okay, so -3 1/2, -2 +2, and 1 1/2, and 2 2/9. So notice on both sides of this vertical asymptote, it looks like we are staying in the upper region of the horizontal asymptote. And that's because everything is getting squared in the bottom and the top is also positive, so this is never going to go negative. This can never turn into a negative number because this is being squared and this is positive. So notice we get something a little different than the typical shape we've been doing. If I wanted to check to see if I cross my horizontal asymptote, remember we take the fraction and we set it equal to 0 over 1 because that's our horizontal asymptote, and that's just 2 equals 0 because 0 times anything is 0. So no, doesn't cross. And like I said, most of the time we don't cross, especially on the ones that we give you. All right, so that leaves us with F, and we did G in class, and H, so we only have 2 more of these to talk through. And H is going to be the only one that has an oblique asymptote. I at least wanted to show you what one of those looks like, but let's do F first. So we need to factor this. The bottom would factor into an x plus 2 and an x minus 2. So my domain is x can't equal -2 or +2. Neither one of those cancels out, so they're both vertical asymptotes. X-intercept, we have an x on top, so that is going to equal 0 at -4. We don't have any holes because nothing canceled out. Y-intercept, plug in 0 for all the x's in the original, and that gives you 4 over -4, which is -1. Horizontal asymptote versus oblique. The bottom degree is bigger, so anytime the bottom degree is bigger, you can't divide equally into the top, so that's when you get 0 as your horizontal, and then that means none for oblique. So if we plot out, there is the y equals 0, x equals 2 different asymptotes, so we have -2 and +2. We have an x-intercept of -4. Aha! So what this tells me is that we are definitely crossing our horizontal asymptote. So that's kind of interesting, but we'll show you that in a minute when we do the little test for it. And our y-intercept is 0, -1. So that's there. Okay, so my things that I care about when I make up my table, remember, are always x-intercepts and vertical asymptotes. That's what helps separate everything. So go from left to right. The first x-intercept is -4. The first vertical asymptote is -2. The last vertical asymptote is +2. You just care about those three things, x-intercepts and the vertical asymptotes. I'm going to pick a value on each side, so -5, -3. We already know what 0 is, so maybe I'll do -1 and 1 in there to get some variety, and something bigger than 2, so maybe 3. So we're going to plug those in, so -5 plus 4. It might be easier to plug it into the pre-factored form, just depends on your calculator. This is -1 over 25 minus 4, so that's 21, so -1/21. Let's see, this one is -3 plus 4 over -3 squared minus 4. That's 1 over 9 minus 4 is 5, so that's 1/5. -1 plus 4 over -1 squared minus 4 is 3 over -3, so that's -1. 1 plus 4 over 1 squared minus 4 is 5 over -3, so that's -5/3. And 3 plus 4 over 3 squared minus 4 is 7 over 5. So -5, -1/21. That's pretty small, but I can't draw it that small, so we're going to go right there. -3 1/5. Aha, notice that's above this x-axis now, so that's where we're crossing through. -1, -1 is down here. Oops. Let me double check to make sure I plugged that in right. I don't think I did. Yeah, let's see, yeah, I didn't plug that in correctly, I don't think. Let me double check though. -1 plus 4 is 3, -1 squared minus 4 is -3. We're probably going to need another piece of information in here because that looks a little bit suspicious. +1 is -5/3, so that is down here. So I'm going to get another point in here between this because usually you don't see two points at the same height unless there's another point in between them that goes up or down. And then 3 7/5. So that's the good thing about these. If you don't like the way something looks, try to get more points because that usually gives you a better idea of the shape. So this one's above. So if I had to guess, I would say that this region's probably staying completely up here in that area. I'm going to plug in -0.5 as well as another x because I want to know what's happening between these 2 points since they're at the same height. And then this is -0.5 squared minus 4. So the top here would be 3.5. 0.5 squared, since it doesn't matter that it's negative, it'll turn positive, and then minus 4 is -3.75. I want to divide that to get a better idea of that point. So that's -0.9. That's what I thought. So -0.9. That means that this is actually kind of like the vertex area. So this is sort of like a parabola down here, just a little bit off-centered. So you get kind of like a parabola shape. And then this one is definitely crossing. Now usually when you cross, you still hover pretty close to that horizontal asymptote. So notice this is still not going far away from that asymptote. It's just crossing through at that x-intercept. Now let me show you that I would have known about this cross if I'd done my little test from the beginning. So you take your function, and you could leave it in the original form if you wanted, since nothing canceled. You set it equal to your horizontal asymptote. This time when we cross multiply, this does turn into 0, but this is still x plus 4. Therefore, you are able to solve for x. So yes, we do cross at -4, which makes sense because that's what our graph showed us that we did. So this one's a little bit more tricky because there's this middle section, but there's also this idea of crossing that horizontal asymptote at the x-intercept. All right, and then the final one that we need to do on this video, because then that'll be a variety of lots of different rational functions, is this one right here. So I believe this top factors, let me see, that would be 2x squared minus x minus 3 Multiply those together, we get -6, and I'm thinking -6 is going to break down into -3 and +2 for that to be a -1. So 2x squared plus 2x minus 3x minus 3. Factor by grouping, this would be a 2x and an x plus 1. Minus 3 would also leave me with an x plus 1. So it looks like the top of this factors into a 2x minus 3 and an x plus 1. The bottom is still just x minus 2, so nothing cancels. My domain is just the one value from the bottom that doesn't work, so that would be a +2. Since that doesn't cancel out, it's also a vertical asymptote. There would be no holes. There are two x-intercepts. There are two separate things on top that have x in them. Add 3 and divide by 2, so that'd be 3/2, 0, and subtract over 1, so that'd be -1, 0. For the y-intercept, plug in 0 for all the x's. You can kind of just look at the equation up here. If you put in 0 for everything on top, you'd still have a -3. If you put in a 0 for the x's on bottom, you'd have a -2. So it's going to be -3 over -2, or just +3/2. Horizontal versus oblique. Okay, so this is the only case I'm doing for you guys that has an oblique, because like I said, we're not going to make you graph one of those, but we could make you find the oblique. So because this bottom is smaller than the top in terms of the highest x, that's when you have an oblique. The way you find the oblique is you do long division. So you divide the bottom into the top. X goes into 2x squared 2x times. We multiply that by everything out front. And then remember, in long division, we do have to change that sign of that row. So then this would be 3x minus 3. And then we say x goes into 3x +3 times. And then you would multiply and finish this out. Now we don't actually care what the remainder is, because this is the oblique asymptote. It's once you get mx plus b up here. So 2x plus 3. So I'm going to show you how to plot one of these, because even though we won't make you plot one on the test, it's important to see that this is how it would happen. You take this and you graph it just like mx plus b. So you go to +3 and you go up 2 over 1, up 2 over 1, up 2 over 1. You could also go down to left 1, down to left 1, down to left 1. Get enough that you can draw a dashed line through all of those values. So this is my oblique of 2x plus 3. My vertical asymptote is at +2. So notice those are going to intersect each other and create sort of a triangle set of regions, and then these kind of odd shapes over here. So our graph's either going to be in these outside regions probably, or they're going to be sandwiched into this triangle piece. Usually there's symmetry involved, so they're either in both of these or they're in both of these. Our y-intercept is 1.5, so it looks like we're going to be sandwiched in the middle because of where that's plotting. And then 3/2 is 1.5, so that's right here. And we also cross at -1. I'm about 100% sure this guy is stuck in this little triangle in here and it's going to be hovering around in that triangle. But we're going to prove it by doing a couple extra points. And then that's all the points I have. So when I go to make my chart, remember x-intercepts and vertical asymptotes get labeled. So -1 is the smallest of those. 1.5 or 3/2 would be the next. And then 2 is the vertical asymptote. So that's my 2 x-intercepts and my vertical asymptote. So I'm going to pick -2 to plug in, something between these. I've already got 0, so maybe just +1. I'm going to have to pick a decimal, so maybe 1.7, and then something bigger. So let's say 3 and 4, because I want to know more about that side than anything, because I have nothing over here. So if we plug in -2, so I'm going to try to do this quickly on my calculator since I'm running out of room to write. This one is 2, I'm going to go with the factored form. 2 times -2 minus 3 is -7 times -2 plus 1 would be -1. So my top on that part is 7. So for this first one right here, this is going to be a 7 on top, and then -2 minus 2 is a -4 on bottom. So that is 7 divided by 4 is about, so this will be a -1.75. So I'm going to be down, which is kind of what I expected. I expected to be stuck right here inside this boundary. If I plug in +1, I might be able to do this down here. 2 times 1 minus 3 over, and then I also have 1 plus 1, because there's 2 factors on top, over 1 minus 2. That is -1 times 2 over -1. That is just going to be +2. So +1 is at +2. Okay, so I'm pretty much 100% sure that I don't even know if I need to do the 1.7. I'm actually going to skip it because this graph is stuck inside here. All of these points are indicating to me that this graph is just hovering inside those boundaries. I don't know though if the other part of the graph is going to be down here or up here, but I'm guessing it's going to have symmetry. So I'm guessing it's going to be in this top half. So let's plug in 3. So 2 times 3 minus 3, plugging into my factored form, over, and then 3 plus 1 also on top, over 3 minus 2. That is 6 minus 3, so that's 3, times 4, so that would be 12 on top, over 1. So yeah, that's going to be way up here. So 312. And then if we plug in 4, that would be 8 minus 3, so that's 5. And that'll be another 5, so that's 25 over 2. So that's 13.5. Or, hang on, did I type that in correctly? Let's see, 2 times 4 is 8, minus 3 is 5. And then 4 plus 1 is also 5, yep. And then 4 minus 2 is 2, yes. So it's 12.5, sorry. So that guy is a little bit higher than the other one was. So what this means is that this graph is probably doing the same thing, but just up here. We don't have enough points or space, but you see the similar range of being stuck inside these two pieces as this one was. So that's sort of what you get when you get an oblique graph. You get these kind of weird parts of the graph that are squished between the asymptotes. Now, just to make sure you know that this one doesn't cross its oblique, because that is a possibility, if you set the original problem equal to your oblique, which your oblique was 2x plus 3 over 1, if you want to think of it as a fraction. If we cross multiply this, this is 2x squared minus x minus 3 equals, and then I would FOIL that out. That would be 2x squared minus 4x plus 3x minus 6. So this is 2x squared minus x minus 3 equals 2x squared minus x minus 6. See how all the x's match exactly? So when you go to cancel and move them over, you just get the two numbers that don't equal each other. So because there's no x left after solving, you do not cross. All right, and like I said, this one's much harder than anything we would make you graph on the test. We could just give you the function though and say find all this information, and that would be reasonable for you just to be able to find the oblique that way. But mainly if you can do the other graphs that were presented, you are you're at the difficulty level that you need to be for the exam for this question. And that's the end of section 4.5.